Dear all, welcome to the presentation on gas power cycles for the subject thermofluid science. In earlier lectures, we had a discussion on introduction and fundamental thermodynamic approach for performance evaluation of Brayton cycle used in a gas power plant. Now the presentation is focused to understand the formulation and method of Brayton cycle, especially to evaluate energy as well as exergy performance. And the specialty of this presentation is that is novelty of this presentation is solutions of this Brayton cycle using JANAF tables, and that means gas property tables. And this presentation is mainly focused on methodology of gas power plant using gas property tables. Basically there are three components in a gas power plant, that's a Brayton cycle. They are air compressor, combustion chamber, and gas turbine. In compressor, the process is adiabatic compression where entropy increases even though there is no heat transfer because of the internal dissipative effects. And combustion chamber, it is a constant pressure process. The temperature is increasing due to combustion process. After that, the high temperature, high pressure gas is expanding in a turbine. The process is adiabatic process similar to the compression. And finally, this is ejected into atmosphere through the stack in case of open cycle, or it may be used, the exhaust gas can be used for heat recovery in a heat recovery for steam generation in case of a combined cycle power plant. Since the focus is given on open Brayton cycle, only gas power plant, these three components are discussed here. The first component is air compressor. In air compressor, the process is initially assumed as isentropic compression process, so that we can get the temperature at the exit of isentropic compression, and later from the concept of isentropic efficiency, the temperature at the exit of compressor can be evaluated. So in the basic thermodynamic, using delta S is equal to 0, that exit temperature can be calculated. That is the relation between T2 by T1 and P2 by P1. That is T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. Now in this isentropic compression, the delta S is equal to 0, but we are taking the properties of entropy from the tables, gas property tables. Let us assume 1 kg mole of air. Out of 1 kg mole of air, 21% is the oxygen and 79% is nitrogen. These oxygen and nitrogen entropies are considered at the temperature, assumed temperature, as P2 by P1. This R log P2 by P1 takes the entropy generation due to the pressure difference. So this entropy is determined with as a function of temperature as well as pressure. The isentropic efficiency of compressor and gas turbine is determined from pressure ratio, specific heat ratio, and polytropic state efficiency. Instead of assuming isentropic efficiency, it is determined from the given data. Compression ratio is generally it is given for a typical gas power plant. Gamma is 1.4 for air. Polytropic stage efficiency is obtained from the manufacturer's data or the design data. After finding the isentropic efficiency, the first step, the exit temperature of air after isentropic efficiency can be determined uh, by assuming initial exit temperature. Initial exit temperature can be assumed from the basic thermodynamics, that is T2 by T2 dash by T1 is equal to P2 by P1 over per gamma minus 1 by gamma. So the initial temperature here, for example, for a typical assumptions, 575.63 Kelvin. At that temperature, we can, after substituting this temperature, delta S can be determined, that is equal to 0.3426. So for basic thermodynamics, this delta S is equal to 0, but using the gas tables, the delta S is not equal to 0 because of this is improved methodology. So this temperature can be iterated till getting delta S is equal to 0 level. So the temperature is changed 575.29. It's slightly it is decreased, and still it is decreased at this temperature. Finally, at 569.19 Kelvin, the delta S is very close to 0 as per our consistency definition 0.01. This is the temperature obtained at the end of isentropic compression using gas property tables. Basic thermodynamics, that's fundamental thermodynamics, is resulting 575.63. In the refined methodology, the temperature is coming as 569.19 Kelvin only. So in the second step, we can calculate the actual temperature after the adiabatic compression process by considering the isentropic efficiency. The isentropic efficiency is defined as uh, isentropic enthalpy rise and actual enthalpy rise. See, this is the isentropic enthalpy rise, and this is the actual enthalpy rise. In this case, H1 is the enthalpy before compression process at atmospheric conditions based on the assumptions. If it is atmospheric temperature and atmospheric pressure, the enthalpy before compression is equal to 0. If this temperature is above atmospheric temperature and above or below atmospheric pressure, this can be determined from the property charts. H2 is determined at the determined obtained temperature of T2 dash from the earlier formula. So we have the details of H1, H2, efficiency of the compressor obtained from polytropic efficiency. So the unknown is H2. H2 is determined by simplification of this equation. So H2 gives the temperature at the exit of compression process. But this is also to be iterated by assuming initial temperature T2, approximately assuming Cp is constant here, since it is approximation, initial gas, and the initial gas, the temperature is substituted in the enthalpy, because this is enthalpy resulted finally. After substituting this temperature in enthalpy equation, or taking using tables, the enthalpy result is 9191.7 out of 9163.2. So here the temperature to be changed to reach this value, the finally at 606.06, a slight change only, the temperature resulted is 9163.8 with the as per the definition of this consistency. So H1, H2 is determined from the following equation, that is 0.21 of enthalpy of oxygen and 0.79 of enthalpy of nitrogen. These enthalpies are obtained from the tables. Again, the tables it is required to do the iteration because the temperatures given in tables are the round figure, that is 600 Kelvin, 700 Kelvin, and so on. After finding these enthalpies, uh, work from the compressor is determined from the equation, that is H2 minus H1. Then the second component is the combustion chamber in gas turbine, that is the gas turbine combustion chamber. For example, if the natural gas is assumed as a fuel in the combustion chamber, natural gas composition can be determined or taken from a case study. Let us assume a natural gas composition here. This is taken from a typical power plant, gas power plant. The reaction equation for combustion chamber is natural gas. This is the natural gas, and air 0 x into 0.21 O2 plus 0.7 N2, where x is the kg moles of air. After combustion, the resultant products are CO2, H2O, O2, and N2. Here we have the values of all the values of A1, A2 obtained from this composition, gas composition, and X is unknown, and B1, B2, B3, B4 also unknown. So there are 5 unknowns. These 5 unknowns can be determined by 5 equations. Out of 5, 4 are mass balance equations, that is C balance, H balance, O balance, and N balance. And the fifth equation is the energy balance equation. So after combining all these 5 equations, well, these are linear equations since it is a full combustion. The values of B1 to B5, 4 and as well as X can be determined. So here the mass of the fuel is generally A1, A2 are in kg moles. To convert the kg moles into kg, the kg moles into molecular weight is multiplied. So the M is the mass of the fuel in kg. Energy of the fuel can be obtained from enthalpy of formation. Obtained is available in the property tables. Energy of the fuel is a higher heating value. In higher heating value, enthalpy of formation of H2O is in the liquid form. In lower heating value, enthalpy of formation of H2O, that is water vapor, is considered as the gaseous form or the vapor form. Similarly, exergy of the fuel is determined from the specific exergy components of this gaseous species, including this gas composition. This is a gas composition. This is the partial pressure component, and this is the base, the standard exergy values. The mass balance of chemical reaction, that is C balance, H balance, O balance, and N balance, results 4 equations for B1, B2, B3, B4. But here out of these 4 equations, X is unknown value. So to solve this value of X, energy balance is required. The energy balance, for energy balance, enthalpy of products, air, that's air, as well as this reactants is required. Enthalpy of air is equal to 0.21 of O2 plus 0.79 of HT of N2, where T is the temperature, corresponding temperature of air. Similarly, enthalpy of reactants is the sum of fuel, enthalpy of the fuel, and enthalpy of the air. Enthalpy of the products is the gaseous compositions, that's CO2, H2O, O2, and N2. So this balancing of this equation, we can get the unknown value of x. Initially, the x value is assumed approximately by assuming the air fuel ratio. Generally, air fuel ratio in natural gas is nearly 50 is to 1. That is mass in terms of the mass, and that can be converted approximately roughly into the kg moles. It's approximately, we assumed here is 30 is initial guess. After substituting this 30 in the energy balance equation, that is the enthalpy of reactants minus enthalpy of product should be equal to 0, assuming there is no heat loss. It's coming area 21,578. So the x value is changed here. After changing finally at 30.82, it's very close to 0. So all 5 unknowns are determined by means of mass balance and energy balance in the gas turbine combustion chamber. The third component is a gas turbine. It's the solution of this gas turbine is very similar to the air compressor. The isentropic efficiency of the gas turbine is determined from the polytropic stage efficiency, and the temperature at the exit of this gas turbine again determined from assuming isentropic expansion. For to solve this isentropic expansion, initial guess is required. That initial guess is obtained from the basic thermodynamic process. That's isentropic process. That's earlier we assumed T2 by T1 is equal to P2 by P1 all over gamma minus 1 by gamma. Similarly, T4 dash is a temperature at the exit of isentropic expansion. For an isentropic expansion process in the gas turbine, the equation is given similar to the air compressor, that is delta S is equal to 0. This delta S is equal to 0. This is the entropy values from gas property, and these are the pressure component. This is entropy before expansion S3. S4 dash is entropy after expansion. These all the values are obtained from the gas property tables. So the initial guess after substituting this T4 dash in this equation, that is T4 dash is equal to 742.35. For a typical example, the delta S is result is 108.31. So by iterating the temperature finally at 823.38, delta S is close to 0, that's 0.01. So this is the process of iteration to obtain the exit temperature after the isentropic expansion. But the temperature is at the exit of gas turbine is more than the temperature after isentropic expansion. So based on this, isentropic efficiency of the gas turbine is defined as the isentropic efficiency is the ratio of actual enthalpy drop and isentropic enthalpy drop. Because actual enthalpy drop is less than the isentropic enthalpy drop, which is reverse of air compressor. As usual, the enthalpies of gas before expansion and after expansion is determined from the properties obtained from tables. So here H3 is the enthalpy before expansion, H4 is enthalpy after the actual adiabatic process, and H4 dash is enthalpy of gas after isentropic expansion. Here H4 is required. H4 is determined from the simplification of this equation. So to find T4 from H4, initial guess is required. So that initial guess is taken from this approximate equation, that's a Cp constant base equation. Again, iteration is started to find the temperature T4 from H4. Given H4 is, this is the value of given H4. By initial substitution of this temperature, we resulted a different value of enthalpy. That's 5,80,250 against the actual value of 5,82,980 kilojoules per kg mole. After iterating this temperature, finally at 879.65, that the enthalpy is 5,82,980. Very exactly is coming, but fraction, by considering the fraction, it is very close to this value. So this is a way to find the temperature at the exit of this gas turbine. Once the temperature is resulted, the actual enthalpy can be determined by taking this T4 in place of T4 dash. So output from gas turbine is H3 minus H4, and output from the input to the air compressor is H2 minus H1. So the net output from the gas turbine as well as this entire gas power plant is WT minus WC. In this equation, MA is mass of air in kg per second. Therefore, the multiplication factor is required in entire chemical reaction to find the values in SI units, that's especially in kg per second, joules, kilojoules, kilowatts, and etc. So the mass factor in left hand side as well as the right hand side, especially to convert the kg moles into kg, is equal for given mass of air in a typical gas power plant MA in kg per second. So mass factor is equal to MA by X into 0.21 m of O2 plus 0.79 m. This is the molecular weight of oxygen 32, and this is the N2 is the molecular weight of nitrogen 28. So this M factor is multiplied in left hand side as well as this right hand side, that's LHS RHS. The power generation is determined in terms of kilowatts, that's mass factor into WC by mechanical efficiency of the compressor. Similarly, the actual output from the turbine is determined from the mass factor, multiplying this mass factor to the earlier output from the turbine, and this is the generator efficiency and mechanical efficiency of the turbine. The net output is as usual, this is the difference between the output, gross output from the turbine as well as this minus compressor input. Thermal efficiency is output by input, that's output is expressed in terms of kilowatts, and input is also expressed in kilowatts, that's multiplying this mass factor and higher heating value per kg, and this is the mass factor into 100. Similarly, exergy is evaluated by finding the entropy at each and every state, that is S1, S2, S3, S4 from the property charts or as well as tables. Exergy is sum of chemical exergy and physical exergy. The chemical exergy of air is calculated from the basic value of standard chemical exergy value of oxygen and nitrogen, and physical exergy of the air at the inlet of the compressor is determined from that is at the temperature, given temperature. Since the temperature is atmospheric temperature, the physical exergy of air at the beginning of the compression is equal to 0. But the physical exergy of air at the exit of compressor is not equal to 0 since the temperature is above atmospheric temperature. The physical exergy is equal to H minus T naught S, determined at the T2. The physical exergy of the gas at the exit of the combustion chamber, that is state 3 is determined by calculating H minus T naught into S at T3, and physical exergy of the gas at the exit of the gas turbine is determined at the temperature T4 from this equation. So the chemical exergy of air is equal to chemical exergy of the gas is determined from the standard chemical exergy of carbon dioxide, H2O, G, gas vapor, and O2 and N2, as well as this partial pressures of this carbon dioxide, etc. So the total exergy is the sum of chemical exergy and physical exergy. Exergy of air at the inlet of the compressor, the total exergy of air is equal to sum of chemical exergy and physical exergy at the inlet of the compression process. Similarly, the epsilon 2 is the exergy, total exergy at the exit of the compression process. Epsilon 3 is the total exergy at the exit of this gas turbine combustion chamber. G4 is the total exergy at the exit of this gas turbine after expansion. So the irreversibility of each and every component can be determined by the exergy balance. The exergy balance before compression is the total exergy before compression is equal to total exergy after compression plus irreversibility of the compression process. So the irreversibility of the compression is equal to exergy, total exergy at the inlet of the compressor, work input to the compressor minus exergy at the exit of the compressor. So irreversibility of the compression, similarly irreversibility of the combustion is obtained from the exergy balance of this combustion chamber. In combustion chambers there is no any work involved, that's why it is only the exergy balance, that is exergy of the fuel plus exergy uh, at the exit of the compression minus exergy at the exit of this combustion chamber. Similar to the exergy, irreversibility of the compression, irreversibility of the gas turbine is obtained by exergy at inlet of gas turbine minus output from turbine minus exergy, total exergy at the exit of the gas turbine. Irreversibility at the exit of the gas, that is exit of the gas turbine, is equal to, that is exergy loss of exhaust is equal to exergy of the gas at the exit of this gas turbine. Exergy efficiency of the finally of the Brayton cycle is defined by exergy output and input. Exergy output is equal to work output from the gas power plant is equal to exergy output, that is exergy input minus all irreversibility loss is equal to output from the gas turbine. The input is exergy input, that is exergy of the fuel, the specific exergy of the fuel multiplying this mass factor uh, from this units, based on these units, and multiply 100, you can get the exergy efficiency of the gas power plant. Thank you for your interest on this presentation.